Next up, we have Matthew Kaney, who will be providing a hybrid talk and live code performance, explaining the theory underlying Uzulangs, which are a family of live code pattern tools.
Yeah, am I good for audio? To plug in. Okay. Yeah. Oh. Okay. Okay. 1 sec. Okay, thank you, Isidore. Again, this is a talk about Uzulangs, functional pattern composition in all senses of functions and patterns and compositions. Now, I am Matthew, and one of the many things I do is I make live coded music and visuals. I'm not actually live coding this. This is sort of slide coding because I don't necessarily trust myself to do it in the time, but we will be looking at some code. And so what is an Uzulang? Basically, once upon a time, this man named Alex McLean made a library for live coding called TidalCycles. It was written in Haskell, a functional programming language, if people are familiar, and attracted a community of performers and live coders. At some point, Haskell is a little bit intimidating if you're not familiar, and the web beckoned, and so he created a new version of the same concept on Strudel, this JavaScript port. And if you're interested at all in live coding, Strudel is a great place to start. And as part of that, now with that port and another port to Python and various other ports and experiments, there is a whole world of pattern languages that are, even though they might look different, are basically based on the same kind of core ideas. And Uzus, named for the Japanese word for spiral, is what we're calling this family. So what is a pattern? A pattern is across some number of dimensions. I'm going to stick with one dimension, and let's call it time. And a pattern is a series of events over time. And because oftentimes patterns repeat, let's measure it in terms of cycles. And so to start with, let me define a little bit of a sort of toy Uzulang. This is kind of what TidalCycles looks like. If you like Haskell, this will make sense to you. If you don't worry. I'm also bored with the code after a fair bit, and then we'll jump to some pictures and sounds. But so, because we want our patterns to be infinitely long, we will represent them as a function of time to events. At any time, you can see what is the event going on in this pattern. Now, time, like I said, we're thinking about taking a cycle and subdividing it. So, so we can call it a query, and we can use rational numbers as our time, and instead of actually querying at one point in time, it's useful to query a little section, kind of slice a pattern up into these windows. And so a pattern is queried on a time span, which is an interval of 2 times. And then it returns events. It can be multiple events in this time span, so we return it as a list. And a pattern can contain any sort of data at all. It's entirely abstract. And so we have a type variable. This is like a generic in any other language. So an event itself is basically a time span and a value. Because for some like technical reasons, most Uzulangs actually will represent time as both the whole of an event, but also if you're looking at just a slice of a pattern, you might only see part of an event. And so you store the whole and the part separately, but for the purposes of our simple Uzulang, I am skipping that. So let's make some patterns. A very simple pattern is silence. This here is my silent pattern, and create a little lambda function that always returns an empty list. Easy, done, here we have a pattern. Now, we might also want a slightly more complex pattern. Here's a function that produces a pattern of one variable as one event that takes up the entirety of a cycle. And like I said, these patterns are infinite. They can go in either direction as long as you want. And this is the point at which implementing this pure function is not that hard, but because you're dealing with sort of queries and parts and intersections of time spans, I'm going to start skipping it. So ultimately, this is not code. This is a picture of text. And so I can make up my own syntax. So bear with me and pretend that these fancy brackets are a way of taking a value and wrapping it in a pattern. Think of it like a list where all of the elements in the list get packed into a, one cycle of this pattern. So some simple things to do, or relatively simple, because again, whenever you query it, you get this list of events. One thing you can do, and yes. One thing you can do is do a sort of mapping. We have a set of a pattern of just numbers, but if we have a function that takes numbers and converts them to notes that are steps in, say, the D major scale, now we have a pattern of notes, and we can take that pattern of notes and we can query it a bunch of times in the background, and then we can send that as basically MIDI notes to our synthesizer, and here we go. Now let's lay over another one. And I'm combining the second pattern with the first by just taking the two patterns, querying them together, and concatenating the events together. If you know functional programming stuff, you might recognize that the mapping is a functor operation. This defines a monoid on a pattern. But also we can take the time spans. These are just numbers, and so we can adjust them. We can do some simple arithmetic. Here we'll add to our query, shifting the entire pattern back in time, and suddenly we have a second pattern that is earlier than the previous one. We can also multiply and create a pattern that's faster than the previous one. Now, a pattern, we have this sense of repetitive cycles, but ultimately, you query at any point, it can be different events, and so a slightly more complicated, but a little more interesting way to combine patterns is pattern concatenation. This is a function where I have two patterns, one on the top, one on the bottom, up here. And my cat function takes a cycle of the first, takes a cycle of the second, queries the first cycle, queries the second cycle, and alternates between those two in the resulting pattern. And then you can start taking these operations and putting them together. We take our fast, we take our cat, we can set it up for any list of patterns, pull the length of the list, speed it up by that much, and now we have two cycles of two patterns squeezed into one cycle of a resulting pattern. We can define a reverse function that takes a cycle of a pattern, swaps the order of the events. We can cat together a pattern and its reverse, and now we have this two-cycle kind of up and down palindrome structure. Now again, like I said, we can take a function, and in this case, now we are taking a note as the first parameter of this in-octave function, and then putting it in a given octave. Octave 3, octave 4, octave 5. But ideally, we would also like to lift this in-octave function up to work on multiple patterns. And this is when things get a little bit more interesting, because again, for functional programming people, you'll notice that I am getting dangerously close to an applicative functor, which is to say a combination of two arguments, both of which are patterns. And actually, there are quite a few ways you could combine the structure of patterns. So we have a series of strategies. And so this lift A2 function basically takes the in-octave function and allows you to pass in one pattern as the first argument and one pattern as the second argument. And it combines the values. And then the strategy that I use, that's this little L above the function. The strategy determines how the different events get interleaved. So this is a left strategy, where basically we take the structure of the first pattern, the left pattern up here in the text, and you'll notice that in the resulting pattern, the first two events both are in the third octave, because those two, at their starts, we look to see what's in the other pattern, and so we have 2 in the third octave, 1 in the fourth octave, 1 in the fifth octave. Now we can flip this, we can take the structure from the right. And now we don't have every single note, but we have every single octave, one after another after another. And of course we can also do an intersection. We can take the two patterns, and every single overlap is a new type of value, and so we return new events. Furthermore, we're querying the patterns separately, so you can start squeezing them together, and a squeeze strategy is what we call this strategy, where now for every single octave you squeeze in every single note. You can also squeeze in the other direction. Oh, I don't have that one. Okay, I will do some live coding. Anyway, okay, well, I'm missing that slide, but there's also a squeeze in the opposite direction, where for every single note you can jump up 3 octaves, up 3 octaves, up 3 octaves. And that's just sort of getting started. Now, the next step, of course, is, and the next step that now I wasn't quite able to put together a visualization of this that fit on one slide. I'm still figuring that piece out. But you can take a pattern of functions, a pattern of pattern transformations. You can apply that pattern to a different pattern of values. You can take, and then that gives you a pattern of patterns of values, and then you can take those patterns, unwrap them, take the structure of the outer one, the structure of the inner one. This is sort of getting into monads, as the functional people will be familiar. And this is fundamentally the core of what's going on in a language like TidalCycles or Strudel. I do, just with a couple more seconds, I will show you some Strudel. In a new tab. So yes. So just so you have a sense of it, Strudel looks very different. It allows you to specify, say, like sample names, for example, and play them, once a cycle. Or you can play them, multiple times a cycle. And like I made up those sort of fake brackets, Strudel uses these sort of string as a kind of domain-specific language, but all of the tricks we discussed are available. We can do this palindrome, go back and forth. And so this is a tool that looks very much like JavaScript, because it is JavaScript. But at its core, all we're dealing with is these patterns of little functions that return events, functions that combine those events, functions that combine those functions that combine those events. And now you have everything you know to make your own Uzu language, or at least understand a little better what's going on with the ones that we have. So thank you so much. Thank you to Isidore and Claire, and thank you all for joining.
Thank you, Matthew. That was really cool. Does anybody have any questions?
How beginner friendly is TidalCycles and Strudel? Like, if I know like CSS and HTML. Like, how can I jump in? Or
I would say that Strudel is pretty beginner friendly. TidalCycles is I like it a lot. I don't think it's that hard. It's hard to set up because it's like a bunch of different pieces of open source software. The nice thing about Strudel is that it's a website. And you can find, there's like documentation on the site linked from there. You can also find a ton of people. I will shout out Switch Angel, Jade, who's an incredible Strudel performer from Boston, does a ton of like videos where she'll live code a pattern and kind of talk through how she's doing it. There's a very, very active Discord for Tidal and Strudel and all of the Uzulang family. And there's a very welcoming community of people who want to explain how this stuff works. So this is the theory. This is the kind of ideas. And actually playing with the tool is, I think, pretty beginner friendly.
Thanks.
Cool.
Hi, thanks for the talk.
Yeah.
Did you say you perform?
I do, yes.
Yeah. When you perform, what are you thinking about?
Ooh, that's a good question. Oftentimes, what I am thinking about is, like, typically I will have a strategy in mind. I will have thought through not necessarily all of the code, but I'll have maybe an idea of the shape of a performance. It's often pretty improvisational, but I'm thinking through, okay, so I've got my pattern of like, my pattern of notes, I've got my pattern of scales, maybe I can throw on some like high level transformation, put the whole thing in a different key. That's interesting. Or, the other piece is that you start to sort of build tools in your toolbox. You have little like tricks you can go to, kind of easy ways to add some randomness, add some, sort of variation. And, I will sometimes, if I'm not sure what exactly is happening, I will, or rather when I'm not sure what to do with what's happening, I'll throw on one of those things. I like to throw on things that are a little random, things that add a little bit of chaos, because that can kind of push you to think in a different way, push you to respond to that.
Right.
Yeah. So when you're actually live coding, it's a lot about thinking through, kind of what are the tricks I know, what are the strategies I know, what parameters can I adjust, things can I add or subtract, what makes, what can I do to move this in the next direction compositionally. Any other? Yeah.
Thank you.
Hi. I was wondering, so when you were showing the sort of 3/4 rhythm earlier,
yeah,
I was wondering, like, if I wanted to add a note so that it was like a 5 and 3 rhythm, this sort of, it would, because the overlaps are happening sort of globally in correspondence to the structures, there's this effect where that addition would sort of affect other notes in the sequence.
Yeah.
Is there a way to sort of, I guess, change these structures so that it's more local if you wanted to do that?
Potentially. Are you saying it'll affect it in terms of like squeezing everything into time?
Yeah.
Yes, absolutely. And that is an interesting kind of new idea that Alex has been playing around, and he wrote a paper on this recently. I'm helping him. We've got a NIME paper coming out that's going to be about like the whole sort of family and universe of this stuff. So yeah, what this approach excels at is polyrhythms, where you like add layers and then they all squeeze into a cycle. And so you've got, 5 events against 3 events. It turns out that all you need to do is assume a meter. Let's say, oh, this is 4 steps. And that just becomes a little field that you stick on your pattern object. You say, oh, this is a 4-step pattern. And it really doesn't matter if there are 4 steps or 5 steps or whatever. If you just say that, then you can implement a different set of combinations or transformations that take that into account, such that maybe if you add your 5th note, it says, well, this is a 4-step pattern, so let's just add it to the 2nd cycle, scoot all of the other notes over, add it to now the middle of the 3rd cycle, scoot the notes over more, and then suddenly you have something where you've got 5 notes, but you're only stepping through them as like quarter notes musically.
Okay. Anyone else? I think we have time for another.
Do you ever use randomness?
Oh, absolutely. That's a huge part of it. We use randomness, which is to say, because we're in pure functional land, kind of the randomness that we mostly use is this sort of noisy function over time. So it's, within the context of a specific time input, it is deterministic, but the output seems very random and noisy. And so you can use randomness to tweak values. You can make some notes louder, some notes quieter. You can also use a sort of signal of randomness at a higher level. And so there are functions that will take a pattern and, remove some of the notes. There are functions that will apply, apply new transformations based on, whether or not your random signal is high or low, that sort of thing. But absolutely, randomness is, I think, a huge part of what makes kind of algorithmic composition compelling and kind of challenging, is that then this allows you to make things outside of your sort of simple little structure.
Great. Well, thank you, Matthew.
Yes, thank you. Are we good to unplug?